Okay, it's my pleasure to introduce now Quentin Boehler. Quentin Boehler is a former CAMI LabX PhD student. He made his PhD in Strasbourg eCube lab. It was in 2016. His subject was on tensegrity mechanism for MR-guided surgery. Quentin is now with multi-scale robotics lab at ETH Zurich. Quentin was postdoc student at ETH Zurich under supervision of Bradley Nason, and now is working on magnetic actuation for medical robotics. Quentin, please.
You hear me and see my screen properly?
Yes.
Perfect. All right, so it's a real pleasure to present today. I would like to thank the organizers to pull that off despite the tricky situation. It would have been a pleasure to be with you in person, but I'm still, again, very happy to be able to present. So I didn't exactly know how to start my presentation today in the first place. As a former, as Joe mentioned, as a former PhD student from the LabX, I figured that I would talk a bit about maybe myself and my journey with the LabX, and yeah, to share with you my experience with the LabX and how I felt about my PhD at the time. So my background is actually in mechatronics. I graduated from INSA Strasbourg back in 2013. And my first contact with the research was during my master thesis that I did with the eCube laboratory already at the time. And yeah, what I did during my master was actually already pretty interesting. I developed a robotic device for magnetic resonance elastography, which is a technique to determine elasticity of soft tissues, such as the liver, by looking at the way a mechanical wave propagates within the tissue under an MRI. And I developed an MR-compatible robotic device to drive a needle inserted within the tissue that can generate the wave in situ rather than externally, as it is done conventionally, as you can see on the left-hand side. And so we had super interesting results. We could use MRI. That was a great project already at the time. And at the end of it, I had the great opportunity to stay as a PhD, thanks to my advisor, that was Pierre Renaud. Yeah, so I stayed for a PhD in eCube, and that was, again, within the framework of the CAMI LabX. So the idea was to have a collaboration with another lab in France, which was the Lyon in my case, in Montpellier, in collaboration with Philippe Poignet and Salih Abdelaziz. And so the thesis was co-funded by Région Alsace and the CAMI LabX. And the objectives of the project was to design safe medical robots that can be compatible with an MRI. So to do that, that had to be remotely actuated, lightweight, and we also added compliance and variable stiffness properties to this device for safety reasons. And to do so, we considered the use of tensegrity mechanism and pre-stressed systems more generally. So a tensegrity mechanism, that's what you can see here, is a pre-stressed assembly of bars and deformable cables that are actuated to perform a task while being compliant. And so my contribution at the time was to analyze their workspace and to provide new standards for their definition. I also did some work on the control. So the very interesting aspect with these structures is that they are parallel compliant structures, so their stiffness and configuration can be controlled independently. And on the design, and also proposed design of variable stiffness components, such as this spherical joint that you can see here, starting from the topology optimization to figure out how to arrange the components in space, and down to the implementation and fabrication and validation of it. And so, yeah, this is now my occasion to, again, give a big thank to the CAMI LabX to give me the opportunity to do that project at the time. And beside the financial support, and that's what Jocelyne Trocaz mentioned at the beginning of this day, is it really created a community I can really felt that at the time, being surrounded by just actually doing the PhD with other people in other labs at the same time. And I think it's a great idea also to foster collaboration between 2 or more labs, which was really, a real benefit for me at the time. And so, as Jeroen mentioned, in 2017, I joined the multi-scale robotics lab. And at the time, and still now, I've kind of tried to keep also collaboration active with former colleagues and members of the LabX. One of the examples is what we did with the Quentin and also with the Pierre Renaud, with eCube and FemtoST on the using similar tools as the one we use for integrity mechanism, but to analyze magnetic continuum robots that I'm going to talk about today. So the multi-scale robotics lab is a pretty big team. There's over 40 people. There is a wide spectrum of activities, but I'm mainly contributing on the activity around magnetic actuation, and more specifically with application to medical robotics, which I'm going to talk a bit more now. So let me first clarify what I mean by magnetic actuation here. So when you submit a permanent magnet to a magnetic field, 2 things are actually going to happen. The magnet going to experience magnetic forces that are created by a gradient of this field across space. And it's going to also experience magnetic torques that are created by misalignment between the field direction and the magnetization vector of your magnet. So essentially, if you control the field and its gradient, you can manipulate the magnet with 5-degree freedom. And that's what magnetic actuation is all about. So yeah, the manipulation of an object with this technology is going to require the generation of a well-controlled magnetic field at the position of the object. And the approach in our lab to do so is to generate such fields using what we call electromagnetic navigation systems, or EMNS for short. And the machines we have to do that in our lab ranges from rather small systems of a few kilograms up to much bigger systems for larger scale manipulation tasks. Now, the other question is, using this machine, you can manipulate a wide variety of magnetic robots. This can be rigid structures, so such as these magnetic modules. So this is a recent example of what we did with these small modules that you can assemble into complex assembly. But the most interesting part with that is to start bringing some compliance and softness into these structures. So the first example is you can connect these magnetic modules by soft links, and you can already achieve quite interesting and complex deformation patterns. You can also have soft bodies that can make the robot adapt to an environment, such as a vessel. And you can also magnetize these structures with the complex patterns, and you can, for example, induce this kind of behaviors, which is a quite complex and functional millipede-like motion that is created under a magnetic rotating field. Now, ultimately, you can also embed magnets along a flexible rod to form what we call a magnetic continuum robot, and that resemble a catheter and endoscope, and that is magnetically actuated in a remote manner. So these structures are can be made very small and dexterous. They can also be made very soft, and they are thus very suitable for increased safety when in interaction with a sensitive environment such as the human tissues. And so for these reasons, this is an interesting alternative to standard catheters and endoscope, and with very promising potential outcome in medicine. And as a matter of fact, way back before I arrived to the lab in 2010, the lab already got a spin-off company called Aeon Scientific, which developed a product along this line of thinking to treat cardiac arrhythmias. And this demonstrated at the time that the technology could be used to perform a clinically relevant task, and actually ultimately propose viable alternatives to standard manual tools. So Our current challenges are toward making more efficient and smaller magnetic navigation systems for other medical applications, and also making better use of medical imaging, as well as bringing automatic features to control the tools. So since Aeon Scientific and the system I just showed you, we notably made a lot of progress on the variety of tools we can use with a lot of different functions, such as laser grippers, video endoscopes. You have a bunch of examples on this slide. And novel features such as variable stiffness properties. And yeah, again, as you can see, targeting a lot of different applications for that. To present our works, I kind of took the habit to look at them with the following pictures in mind. So where these technologies I just show you are the cornerstone of the research we're doing, and which development is motivated by application-specific problems. So I have only 30 minutes today, so I selected for these applications only 2 examples that I hope is going to illustrate well the concept I want to share with you, and namely cardiac interventions and retinal surgeries. So one of the applications we targeted last year, I mean 2 years ago actually now, was to use these technologies for subretinal injections, which is a therapy that is seen as the future to treat retinal diseases. It consists in delivering viral vectors or stem cells into the subretinal space. So the subretinal space is located behind your retina, which is this kind of outer layer of your eye. So which is a sensitive part of the eye. And so this is a very delicate task, require micrometer precisions, and for a surgeon to remain stable for possibly several minutes. So the idea to bring magnetic actuation to that was to bring flexible magnetic tools for increased safety and precision. So we have this tool which is composed of flexible polymer tubes with a magnet at the tip, and inside the glass capillary to deliver the drug, and the laser that we use to detect the tip of the tool. So this is the setup. We have these electromagnetic navigation systems on the right-hand side, and we did experiments on both on plastic mock eye and excised pig eyes. And so we controlled the insertion of the tool within the eye with a piezo positioner. And yeah, in this video you can see an example of manipulation. So the outer diameter of this tool is 300 microns. You can see here the insertion with the piezo positioner. I'm going to talk about that later, but we also use models both of the eyeball, the AMNS, and the tool to control it. And yeah, we could do some control. So here the user is controlling the target point of the tool, and we control the tool and the machine so that the tip is actually following the target. And then eventually you manually control the insertion of the tool, and it's going to just follow the target and ultimately reach the target point of the retina, and then you can inject and deliver the drug. And you can see that on the pig eye here, and we characterize that under OCT imaging. So what you see on the right hand side is the cross section of the eye, and the kind of the delineation is the upper layer that you see here is the retina. You see the needle being inserted in there, and the liquid being delivered, creating this blob. So what I really like about this example is that it really shows you how we can exploit how soft and small we can make these tools, and we can also use model for automation. And this one, it really constitutes a safe alternative to rigid tools. Now, the other example I wanted to talk about is about heart intervention. So it's a much more exploratory thing that we did last year, which consists in developing magnetically active cardiac patches. So the idea here is to place patches around the heart wall to assist the pumping, which is the main function of the heart. So because essentially some people suffer from a lack of pumping performance. So the idea here is to provide a few hours every day pumping assistance to the heart of the patient. And so, yeah, we tested that with different arrangement of the magnets, and you can see here we tested on pig hearts again, and the two tubes are inserted into the two ventricles of the heart, and you can see by applying some fields, you're going to be able to apply this contractive patterns on both ventricles and basically pump blood out of the heart. And what we show in this example is that depending on how you arrange the magnets on the heart and how you actuate the field, you're going to be able to have different pumping patterns with the two ventricles. So again, this is very early stage compared to what I showed you before, but I think that illustrates quite well how you can use this magnetic technology to actuate in a completely remote manner and still create quite complex deformation patterns. In the meantime, we are also tackling more fundamental aspects, and the core of them is the ability to model these systems to predict their behavior. So remember here that we have two pieces of technologies, an electromagnetic navigation systems, which is the machine to generate the fields, and the magnetic tool that is to be submitted by these fields to perform a task. And regarding the modeling of EMLS, so the machine to generate the fields, the early works in our team consisted in using a linear approach to model the field generated by the magnets. So for that, it's pretty simple. You consider each of the electromagnets to be a dipole model, and you basically just do a linear superposition of all of the electromagnets. So here I is the current vector, so it's all of the currents in the different electromagnetic stack on the vector. And it is mapped to the field generated at one position, so B at position P, by a very simple relationship, which is just what we call an actuation matrix, which is called here A of P. However, this approach is limited when you consider bigger systems with magnetic cores that are going to be saturated when you increase the currents. And that leads to some non-linearities that we're going to have to capture at some point to have a precise model of the system. And you can see on this picture here the linear model that deviates from the real measurements when the currents increase. And very interesting things that we did last year was to use more complex modeling strategies to have a better to increase the accuracy of our prediction. And one of the things we did is to use machine learning methods to do so. So to do that, we had to collect a lot of data. So we trained the models by measuring, by collecting magnetic field across space with this array of magnetometers. And we basically just varied the input of the system, which are here the set of currents. And yeah, we trained models with different types of models. So the blue line here is the linear model I showed you. So you can see the error. So I should mention that the vertical axis is the error on the magnetic field. So it's the mean absolute error on the magnetic field magnitude. So the MPM is the linear model I showed you. So you can see that the error increases drastically when you increase the currents, and you can basically make the model much more accurate at these currents when you consider both artificial neural networks and convolutional neural networks, so ANN and CNN. So again, quite interesting results here. Now, the other half of the modeling that I mentioned is modeling the soft tools that are submitting to these fields. So our original models are based on continuous curvature models and cost railroad models. And you can see here in the video our original implementation of the cost railroad model with fixed length in free air. However, you have several limitations from this approach. And what we did to have a better model that can be more usable for applications later on is to add collision environment and variable length to these models. So SOFA has been mentioned this morning already. We collaborated with Hugo Talbot and Christian Durier to use their simulation platform and the plugin dedicated to model beam-like structures such as endoscopes and catheters. And we just added up the physics related to the magnetic actuation and integrated it within our current software platform, and that went quite well. And ultimately, we had a lot of advantages over the previous approaches. You can dynamically adjust the meshing of the beam so that you can vary the length of the tool. You can detect and account for collisions. You can even take into account friction forces. And what we're doing right now is actually consider to use these models to do some control using inverse modeling. And actually, something that was surprisingly good is how well these simulations can match our experiments. So we did some tests in flat structures, and that worked really well, as you can see on this video here. Now, ultimately, we want to use these models for real applications, obviously. So what we believe constitute a very interesting applications for these models is endovascular navigation, on which we are mainly focusing right now. So it consists in steering tools magnetically under X-ray guidance to reach brain vessels and treat brain aneurysm, for example. So we aim at using these simulations in two ways: to develop training exercise for surgeons to learn how to manipulate the field and the tool using evaluation metrics. So this is the example you see here, where you have this PS4 joystick in the hand and you control the system as you would control the real system, actually, but in a very like a game-like manner to reach dots in a rigid vessel model. And we also do develop more realistic simulators. So what you see on the left-hand side is actually a neurosurgeon using our system in a silicon phantom. So to reach the brain vessels coming from the aortic arch, that's what you see on the fluoroscope picture. And what you see on the right-hand side is the surgical simulator, which matches, well, kind of looks exactly how it would be in a real case. And yeah, so what's next with all of these? So obviously we are mainly driven by bringing these technologies to the operating room. So the natural extension of what I've just showed you today in that respect is to work to make these systems more clinically ready. And actually, most of these developments, including the development of EMNS and specific and robust tools, I couldn't really mention today for confidentiality reasons, but we're still doing a lot of work on that. And also propose a realistic training environment. And to do that, what we envision is to couple what I just showed you before with a visualization environment, for example, using Unity. That's what this Infinity Tech 3D company is mainly doing, for example. And the other part of the job is to add more features. So an example, we want to use a lot medical imaging. And what the video you see here is how you can overlay the magnetic fields that are created by the machine on an X-ray view. And we do that by just registering the X-ray machine with respect to our machine. And so again, a lot of exciting stuff to be done on there. So yeah, I wanted to thank you all for your attention. A really big thanks to the Multiscale Robotics Lab team. Obviously, what I showed you here is most of the time is way beyond what I've done just by myself. So yeah, big thanks to them. And I'm open to questions.
Thank you, Quentin. Thank you very much for this outstanding presentation and for all those impressive results. Obviously, magnetic navigation is a powerful means for guiding surgical tools for minimally invasive surgery or vascular or cardiac surgery and so on. Thank you very much. We got a lot of questions on the chat, so I will take them in order. Taha first. Taha is wondering the possibility of multi-point actuation. Is that possible to have a device which is magnetically actuated with several independent sections independently actuated? Is that possible? Is that not a big limitation of magnetic navigation?
Yep. So one of the big problem with the magnetic field itself is it's not that easy to generate independent field at different position in space. It's just a degree of freedom problem, but essentially with 8 electromagnets, you can control the field that is radiant at one position. So you can imagine how the number of coils that you need just, you know, just blow up if you try to control the field at much locations. The thing that we did though to tackle this problem is actually to have variable stiffness devices. I can actually go back to this one. So we developed like catheters with several sections that you can make either soft or rigid, and with different magnets disposed along them. So this is this video here. I don't know if you see my cursor. This is the bottom left one.
Mhm.
And you can shape successively each of the sections. Obviously, it's less perfect than controlling independently all of the sections at once, but it's a very good and viable alternative to do so.
Okay, thank you. Pierre Renaud is wondering what are the possible transfer for this technology?
So to the clinics or
clinic or industrial, I don't know what clinic maybe. What are the possible future clinical transfer for this?
If you had to bet on one application, what would be your favorite one?
So it depends. It's a very difficult to answer. This is we kind of pulling our hair out on this one recently, because we think we have a lot of potential in a lot of them, especially endovascular and upper and lower GI navigation and treatment. I believe there is a lot of potential for endovascular, but it's more a business question actually. It's much harder to penetrate, and it's also a risk versus usefulness thing. Obviously, endovascular is much more risky because you basically navigate into the brain. For the GI though, it's easier to do proof of concept even in vivo, but the potential is probably less interesting for the medical doctors. This is a super interesting discussion, but this is way beyond what I'm talking about today. But definitely the right question to ask yourself for sure.
Okay. In your conclusion, you tell about portable systems.
Mm-hmm.
This is linked to the Bernard Bay question. Bernard is asking, is that necessary to have so big magnets for very small tools? I saw one of the system you presented is something 7,000 kilogram heavy.
Right. So that's a very good question. So one of the first system issue. I'm trying to get back to the slide. So, whoops. No, that's after. Sorry. No. Sorry. I'm just trying to get back to the slide where I show all of the systems. Here. All right. So the Aeon Focus is the big machine that Aeon Scientific developed back in 2010. And the problem with that, and the reason why they actually couldn't really sell the machine so properly, is that it requires a whole OR to put the systems in. Now, the system that you see on the upper left is the Octomag, and you see that you need fairly big magnets for a fairly small workspace. What we did in the meantime to have kind of the same performance as the big system but in a smaller one is to improve on the design of the coils, and that's specifically one of the aspects I can't really talk about today, because this is one of the main IP we have, is to really improve on how well these coils can perform, how well they can be cooled down, because obviously you have a lot of power going through there, so you need to cool down the coils. But yeah, the mechanical design of that is really challenging.
Okay.
I don't know if I answered the question, but yeah.
Okay. So I guess we have time for last question. Philippe Cinquin is wondering what's the level of forces you can produce with such system. I guess the question is linked to cardiac patches and their weight.
Yeah, so just to be careful on words, when we talk about forces, remember that in that case, the forces are generated by the gradient of the field. And just in practice, the forces you can apply in an object are fairly small. If you consider a catheter example, the forces are just neglected because the gradients are just not high enough. So we mostly consider gradients to apply forces, like magnetic forces on untethered objects, as you can see on the video here. For catheters, or even for the patches, the way you apply like a mechanical actions on the hearts is actually through the torques. So because basically the magnets are going to try to align with the field. So the field is going up and down here. And with the magnetization, you just tend to align the magnets and you actually apply torques on the heart wall, not forces really per se. I mean, again, it's a matter of how you design your device. But in that case, it was quite realistic. Well, obviously the magnets are quite big here, but we believe it was quite realistic to have this just hard magnets on the heart wall and use system that we already have to generate these forces or torques or whatever you call them. Mechanical actions, I would say.
Okay. Thank you again for this nice presentation and discussions.